Hello everyone, this is Srinivas Chakravarti, Assistant Professor, Department of IT, Sri Vidyaniketan Engineering College. Today we shall discuss about an interesting problem, the traveling salesperson problem and dynamic programming solution to it. Initially, let us glance about dynamic programming strategy. Dynamic programming, in short DP, strictly follows the principle of optimality. According to this principle, it doesn't matter what the previous decisions you have taken and their sequences, but forthcoming decisions ought to be taken such that the sequence of decisions should lead you to optimal solution. When it comes to the traveling salesperson problem, in short TSP, it's all about a salesperson's travel to several cities using shortest path. He can start from any city, provided each city is supposed to be visited only once and he must return to the starting city. If there are n cities, then possible paths of travel is n factorial. This definitely crosses the problem to grow exponentially but not a polynomial one. It's clearly a permutation problem but not a subset problem. To represent the TSP problem mathematically, we use a graph G with vertices V and edges E. And the cost of edge from vertex I to j is Cij. We understand that the solution for TSP is just a Hamiltonian cycle in the graph with minimal tour cost. Consider an instance. If the tour starts and ends at vertex 1, then every tour consists of an edge 1, k, where k belongs to the set V minus vertex 1. And also the path from k to vertex 1 exists. This path goes through each and every vertex in the set V minus 1, k vertices, but exactly once. Now let g of I, s be the length of the shortest tour starting at vertex I. This path goes through all the vertices in the set S and terminates at vertex I. Then g of 1, set V minus 1 will be the total length of optimal tour. Following the principle of optimality, g of 1, set V minus 1 is equal to minimum of C1k plus g of k, set V minus 1, k, where k varies between 1 and n. Let us call this equation as 1. Now, generalizing this equation 1, we have g of I, s equals to minimum of Cij plus g of j, set s minus j, where I is the initial vertex and j is the destination vertex, and j belongs to set S. Let's call this equation as 2. We also understand that g of I, null is equal to Ci 1, where I lies between 1 and n. Hence, the size of set S is 1. The size of set S grows linearly up to n minus 1. Let's work out an example. The adjacency matrix given is the cost of the travels between the cities. From the matrix, we understand that number of cities n is 4. Let the S grow from null to n minus 1, that is 3. So when the size of set S is null, g of 2, null is C21, which is 5, g of 3, null is C31, which is 6, g of 4, null is C41, which is 8. When size of set S is 1, g of 2, set 3 is C23 plus g of 3, null, which is 15. Similarly, g of 2, set 4, g of 3, set 2, g of 3, set 4, g of 4, set 2 and g of 4, set 3 are calculated, whose values are 18, 18, 20, 13, 15 respectively. When the size of the set S is 2, g of 3 set 2, 4 is equal to minimum of C32 plus g of 2, set 4 and C34 plus g of 4, set 2. Similarly, g of 3, set 24 and g of 4, set 23 are calculated, whose values are 25, 25, 23 respectively. Finally, the size of set S is 3, that is n minus 1. G of 1 comma set 2, 3, 4 equals to minimum of C12 plus G of 2 comma set 3, 4, and C of 1, 3 plus G of 3 comma set 2, 4, and C14 plus G of 4 comma set 2, 3 is calculated. The minimum value of the optimal torque cost of the TSP is now calculated as 35 in the example, and the path of the torque is starting from vertex 1, next to vertex 2, next to vertex 4, next to vertex 3, and finally returns to vertex 1 again. This is how we compute the dynamic programming solution for traveling salesperson problem. Thank you.